Well, hello there. We're going to have a look at determining the rules for cubic polynomials now. Now, this is very similar to a few videos ago, where I did the same thing from looking at the graphs of quadratics, the graphs, and I split them up into 5 different types. And we used the template equation for each type then to substitute known points in to get the actual rules. Well, this is very similar to that process, except we're doing this for cubics, okay? Now, in this video, I've started off with the worst one first, where we're just given 5 random points, I think. How many pronumerals do you have in a cubic? ax cubed plus bx squared plus cx plus d, isn't it? Wait a minute, is that right? Let's have a look. I'm just going to get this right. Yeah, 4. So you need 4 equations in 4 unknowns if they're just 4 random points. So if you were to imagine having 4 random points given to you on a graph, yes, then you would need to solve 4 simultaneous equations if they weren't significant points like, intercepts or that kind of thing. So this is an example of that. It's pretty bad. So we're going to solve this, you and I are, and we're going to solve it simultaneously for A, B, C and D. Now, don't worry, look, I'll show you. I'm going to show you because a lot of students are mystified and very overwhelmed by this process. It's very simple, it's very systematic. We will do it together. Come on, you and me will be partners. So solving each point substituting each point in turn, what do we get? So that's the first one. I've substituted 1 and minus 2. Now I'm just going to clean all that up in a minute, right? Oh, actually it's cleaned up, isn't it? Yes, it's all right. I've already done it. Now, minus 1 and minus 10, that's the second point, the second equation. Here's the third one from 2 and 2, and the fourth one from minus 2 and minus 26 gets us that equation. Now we've got to solve all those 4 equations simultaneously for A, B, C and D. Well, this is going to be quite an epic, so let's go. From 1, now what I've done there, guys, I'm going to use the process of substitution. So in equation 1 I'm going to substitute for A in terms of all the rest of it, the B, C and D, and then I'm going to put that expression, or that expression for A as minus 2 minus B minus C minus D into equations 2, 3 and 4, which will then become my working equations, and then I'm going to repeat that same procedure till I get down to 2 equations in 2 unknowns and solve them, and then work backwards to work out what the other variables must have been, which I had previously substituted out. Now, this is what you get, substituting to 2, 3 and 4. So that's equation 2. What's written in red there is what was it? A. Yeah, A. Now, wait a minute, have I done that right? Let's have a look. Yeah, that's right, because we're doing it in equation 2, and that was minus A in equation 2. So now we better clean that up. Okay, that's cleaning it up. Divide through by 2. B plus D equals minus 6. That's equation 2A, or daughter of or son of equation 2. Now the equation 3 process, doing that, we get that, and we're going to have to clean that up. Clean away today. Yes, we get all that. It's still, probably can't do much with that. That's equation 4 now. I've done it into equation 4. And yes, that's going to take a bit of cleaning. Fixing that up, just simplifying it a bit. Simplify now. Is there any? Yes, we can simplify it a bit further, and we get to that now. Can't really. Can I cancel that? Yes, I think. Yes, I can cancel divide by 3. So we get that. Okay, always divide through if you can, because otherwise you get telephone numbers in all this stuff. So that's what I've done now by substituting out from equation 1 and sacrificing equation 1 as a working equation for the rest of the process by finding A in terms of the others, substituting that in 2, 3 and 4, getting 2A, 3A and 4A. Now, we're going to do the same thing now. We're going to take one of those equations, and this time I'm going to substitute B out of the consideration. So B would be minus D minus 6. So I'll put that into, sacrifice that equation as a working equation now, put that into 3A and 4A. Not as B anymore, but as minus D minus 6. Okay, here we go. So that's what happens when you put it into 3a. Have a look, see if you agree. Yes, it's good. That gets you that. Cleaning it up, you get, and cleaning up a bit more, you get that. Now that's 3b. Okay, 3b. Now I've got to do the same thing in 4a now to get to 4b. You get the process. I've got to go over the screen now. Yes, so that's from last screen. Here we go, cleaning up, and we get that equation. Now let's just summarise where we are, because it's getting very complicated and we're going to keep our heads together here and not give up. So that's equation 3b and 4b. Well, that's actually very simple now, guys, and look how easy that's going to be to solve. I can now do the elimination on that by adding up those two equations, and I'm going to get 4c equals 12, therefore c equals 3. Yippee, 3. Mr. C is 3. Now I can basically do a very quick little bit of a check in here to work out what D must have been, can't I? Substitute that into, I'll substitute 3 into 3b, okay, that's fair enough. And what do we get? We get that, 2 times 3 plus D equals 2, therefore 6 plus D equals 2, therefore D equals minus 4. Yes, minus 4. Now that's terrific. So now we've got C and D. Now we can go backwards now and find an equation which had an A and a B in it, or just a B or an A with C and D or something like that. There's one. There's one. So B plus D, yeah, that's got a B in it with a D, right? So we can work out what B must have been now from that one, yes? So B plus B is equal to minus 6, therefore B minus 4, because that's D is... D is minus 4. Therefore, B must have been minus 2. When you solve that for B, you get minus 2. We're nearly done now, guys. We're nearly done. Isn't it fun? So now we'll go back to find an equation with A in it, where A is the only unknown. That looks pretty good. Yeah, good. And we just substitute in for B, C and D, and we can get, looks like it's going to be 1 to me. Yes, excellent. A is 1. So look, we did it with a minimum of pain. There is our equation for... Okay, now I just accidentally had a 2 there instead of a 3, so I just fixed that by pausing the video. Now, that's right now. Everybody good? Everybody okay? Happy? Right, well, let's push onward, ever onward. Yeah, this shows how to solve a set of 4 simultaneous equations by substitution, but it is long and involved, and it is far more complicated than you would get in a tech-free exam. All right? Does that make you happy? But it is good for skill building, and that's why you should do it. Now, using CAS, just have a look at this. We put the equation in as f1 of x, then we basically go to algebra and solve system of equations, and then we select 4 equations, and we then type in A, B, C, D for the 4 variables that we want, right? Then we basically do this. We do this. We say solve f1 at x equals 1 equals that. That's the y value. And similarly for the other 4 points that we substitute in, we're solving for A, B, C and D, and look what happens. Look at that. It's absolutely amazing, isn't it? Calculators are great little things, aren't they? Yes. And when you consider that these calculators will have far more computing power than the computers they used in 1969 to land people on the moon, it's absolutely mind-boggling, isn't it? The age of technology is well and truly upon us. So, intercept form. Okay, now let's go with this. We're going to find out the equation of a cubic, which is in intercept form, which has single linear factors. Right? That's the template. That is the template. And we've got 3 intercepts plus 1 other point are needed to solve for A, B, C and D. So here's one. Right, now you've got to look at that and you've got to say, well, do they give me the intercepts? Yes, yes, yes. And do they give me another point? Yes. So intercept form is the way to go, right? You use that. You put your x-intercepts in, as I've done there, making sure that you don't mess the minus 4 one up, because that'll be x plus 4 in that case. And then you basically have that, and then you substitute your other point in, which was 0 and 4, the y-intercept. Plug away, plug and play, and you save the day. You get basically A is a quarter, and there's your equation. Yeah, it's just fantastic, isn't it? So there you go. What's this one? Now this is intercept form with squared, an example of some squared linear factors, and one just straight linear factor, okay, making up the cubic component. So 3 intercepts, yes. So we've got 3 intercepts, I'm saying there, from the squared repeated linear factor plus the intercept corresponding to the straight linear factor. That's really 3 intercepts, if you like. The squared one making up the equivalent of 2 and the straight linear one making the third one. And one other point are needed to solve for A, B and C. Now here's an example. Look at this. That's a squared one. Because at this point the graph just comes down here at -3, x is -3, and it zooms away without cutting through the x-axis, right? So that is a squared linear factor. That'll be x plus 3 all squared. This one will be x minus 2, because that's a straight cutting through one, a straight linear factor. And this one here will give us our dilation factor, the A factor, okay? Yeah, got it? So that's the template we're going to use for this case, okay? That's the squared linear factor, that's the normal straight linear factor. Put in our intercepts, okay? And away we go, right? That's what it's going to be now. All we've got to do now is substitute this point in here, and we've got the value of A. Okay, there it is. Substitute it in, and it looks to me 3 squared is 9, 2 is 8. It's going to be a half. It's going to be a half. It's going to be minus a half, because this is an upside down cubic. Okay, it's coming in from the top end, going out the bottom end, instead of the way a normal positive cubic would do, coming in from the bottom end and go out at the top end. Yeah, so we've got it done, guys. We've got it done. We've got it where we want it, and there's our answer. There it is. See? It's terrific, isn't it? All right, now, have I got any more for you? Yes, it looks like I do. This is intercept form with cubed linear factors. Now, have a look at this. There's, okay, if we have a cubed linear factor, we have a stationary point of inflection, right? And because we've got no translations up or down to add to this, it's all going to happen on the x-axis. You'll see what I mean. The intercept corresponding to the cubed repeated factor and one other point are needed to solve for A and B. So there's an example. See how it's all happening on the x-axis? There's a stationary point of inflection. That's where the cubed linear factor is. I can tell you right now, that's going to be, is that 3? Yeah. That's going to be x minus 3 in brackets all cubed, and then times A, because there's going to be, we have to work out if there's a dilation happen from this other point here. Do you get the idea? Yeah, good. So this function has a cubed repeated factor in it of the form that. Yes? Where B equals 3. Of course it does. So now we've just got to find out the value of A by substituting this other point here. Yeah, and let's do that. So it's substituting 5 and 4, x is 5, y is 4, the other point, and we do that, and we get that, and we get A as a half again. Yes? So there's our final finished product. Yes? It's great, isn't it? So I know, I get very excited when I see these things. They're fun. So perfect cube form. This is perfect cube form where we've actually translated this thing up a bit by a factor of c, okay? So this cubed linear factor is no longer happening as an intercept on the x-axis anymore. It's just the stationary point of inflection of the thing, okay? I'll show you. The stationary point of inflection at B and C, yeah, that's the stationary point of inflection. Here is the x and here is the y, because that's how the thing from x cubed has been translated over to the right by B in the x and up by C in the y, right? And we need one other point to work out any dilations. So have a look. There you go, look. You see? So look, that point there is 3 and 2. So what is the B is 3, the C is 2, isn't it? Yes, there we go. And we substitute the other point in, and we get the value of A as, what's that going to be? 11 minus 2 is 9 over 2, it's third. It's going to be a third. A third. Yes, there you go. There's your answer for your graph, okay? Now you can see how to do these now. They're very, very straightforward, aren't they? Yes? I think that might be it. Yes, there's Mr. Star. Hello, Mr. Star. Huzzah, Mr. Star. And you'll go far, of course, as we all know, if you do plenty of practice. All right, off you go. and do some practice. And have a wonderful time, and we'll see you in the next exciting instalment. Bye.